Hi folks, today we're going to learn about graphing linear equations in slope-intercept form. So this is a new form of linear equations. We did standard form last time. And so it's important to know what slope-intercept form looks like. It looks like this: y equals mx plus b, where m is the slope and b is the y-intercept. We've already talked about what the y-intercept means. It's where the graph crosses the y-axis. But we haven't talked about slope yet. So let's look at some definitions for slope. Slope is a measure of the steepness of a line. It's a rate of change between any 2 points on the line. And there are different ways to think about this. Slope is abbreviated with the letter m. Some people describe it as being rise over run. Well, what do we mean by rise? Rise means going up or down, and the rise is a measurement in the y direction, whereas run is your horizontal movement, the measurement in the x direction. So another way about thinking about slope is thinking about the change in y over the change in x. To do that, to be consistent, to make sure you're always measuring in the same direction, slope is given, the formula for slope is given using this formula here: y2 minus y1 divided by x2 minus x1. It doesn't matter which point you decide is point 1 versus point 2, so long as you're consistent throughout. So let's practice a couple problems with slope first to show you what I mean. So if we come down here for part A here, describe the slope of each line, then find the slope. So with describing the slope, this has to do with kind of describing functions that we did a few lessons ago, but it's describing the slope as being increasing or decreasing, a positive slope or a negative slope. So positive slope is when the line rises as you go from left to right. The same way you read, going from left to right, is what we're talking about here. And then the negative slope is when the line falls from left to right. So here I would describe this as having a positive slope, because as I go from left to right, I go up the hill. The line rises from left to right. Now that I've described the slope of the line, now I'm going to find the slope. I'm going to actually calculate the rise divided by the run. So let me just scroll down a tiny bit here so I've got a bit more space. Rise over run. The rise, in order to determine the rise, I need to pick 2 points. So I'm going to choose this point here, which is -3, -2, and this point here, which looks like it's at 3, +2. Okay, so I picked 2 points on the line, and what I need to do now is figure out the rise between points 1 and 2 and the run between points 1 and 2. So just for consistency's sake, I'm going to call this point 1 and this point 2. And when I go from point 1 to point 2, I have to go up 1, 2, 3, 4 units. So my rise is 4 units. And my run is 1, 2, 3, 4, 5, 6 units. So my slope is going to be the rise divided by run, 4 divided by 6, which simplified gives me 2/3. Notice it's not enough to just count tick marks. On this particular graph it works because each tick mark is worth 1. Like this is 0, 1, 2, 3, and in the x direction this is 0, 1, 2, 3. In this case, I was able to just count tick marks, but it's important, you need to watch out for skip counting on the x and y axes. If you're just going to kind of count the squares, you need to be sure that each square is worth 1 before you just count it as 1. And that's going to come into play when we get to example 3 over here. First, let's look at another example, this time with a different slope. If you look here, as I move from left to right across the graph, the slope goes downward. This is a negative slope. and I expect to see a negative sign as when I calculate the rise over run. So let's see, if I call this point 1 and this point 2, so that I can be consistent, I measure the rise as I go from point 1 to point 2 and the run as I go from point 1 to point 2. I can see here that this is a fall. So I go down 1, 2, 3 units. So the rise is -3 because it's not actually a rise, it's a fall. So I use a negative number to represent that. And then the horizontal movement, the run, is in the positive direction, 1, 2 units. So my slope here is -3/2. Please do keep your slope in fraction form. It makes it much easier to redraw the graph later on if you know what the rise versus the run is. Converting it to a decimal, writing this as -1.5, you would lose that information, and it makes it harder to redraw the graph later. I can't spell slope. Let's see. This third example here, this is a positive slope because as I go from left to right, the line rises. So this is going to be a positive slope. And here I need to be a little more careful. Notice that each tick mark is not worth 1. This is 2, 4, 6, 8. So each tick mark is worth 2. So I can either be careful when I'm counting my units as I go from point 1 to point 2. I can be really diligent and careful about counting my units. Also, this one's a little awkward just because it's not right on the tick mark. It's kind of between the -2 and the -4 mark in the y direction. If I'm exactly halfway between, it's easy enough to say that I have a y value of -3. But I'd like to have a more consistent, a more reliable way of calculating slope that doesn't necessarily depend on me being able to count off the tick marks on the graph. In case the graph is really big, the numbers are really big, it gets painstaking to just count the units. So I'm going to use a different method. I'm going to use this equation that we looked at up here, y2 minus y1 divided by x2 minus x1. So if I write that equation here, y2 minus y1 over x2 minus x1, I've decided what my point 1 and point 2 is, so I just need to plug in those values for, this is point 1, so this is my x1 and my x2. I'm sorry, my x1 is 2, so plug that in here. And my x2 is 5. My y1 is -3. Oopsies, sorry. -3. But I have to subtract that from y1, which is 4. So notice what I did. It doesn't matter which point I label as point 1 or point 2, so long as I'm consistent in labeling my 2 and my -3 both belong to point 1. So my 2 and -3 I wrote in the kind of the right side of the fraction, and then my 4 and my 5 I wrote at the left side of the fraction. Do be careful with your negative signs here. There's a negative sign in the equation, so it's important for me to keep the negative sign, but there's also a negative sign in the point that I got off of the graph. Both of those negative signs are necessary because when you subtract a negative, it's like adding. So I'm really going to do 4 plus 3, which is 7 on the top of my fraction, and 5 minus 2, which is 3 on the bottom of my fraction. And this fraction is already in lowest terms, so 7/3 is my slope for this example. So what do we do if we don't have a graph? We saw that it's reasonably straightforward to count squares if we are given a small graph. And if we're given a large graph or an awkward graph, we can use y2 minus y1 over x2 minus x1. What if we don't have a graph at all? What if we have a list of data points? There are a couple strategies here that you can do. One thing is you can look at your table of data and you can see if the data are regularly spaced. So as I go from 4 to 7, that's plus 3. As I go from 7 to 10, that's plus 3. As I go from 10 to 13, I'm adding 3 to the y value every single time. Similarly, in the y direction, as I go from 20 to 14, I'm subtracting 6. As I'm going from 14 to 8, subtracting 6. 8 to 2, I'm subtracting 6. So how do I put that together to get a slope? Well, remember, slope is the change in y over the change in x. Well, each step here, I have my change in y is negative 6, and my change in x is positive 3. So together, if I combine that y value and that x value, I get a slope of negative 2. Now that's kind of a lot of work there to make sure that, I don't know, the slope is consistent. You don't actually need to check every single value. It's okay to just check one value, like going from negative 1 to 1 is adding 2, and going from 2 to 2, well, that's not doing anything at all. Now, this is assuming that these are linear, okay? I've already told you that these are lines, and so you can assume it's linear, so you don't have to go ahead and check other examples. However, in this unit, we were learning to tell the difference between linear and nonlinear functions. So it might be a good idea on a test just to confirm that this is a linear equation, and see that, yes, when I go up by 2, I still go up by 0. When I go up by 2 in the x column, I go up by 0 in the y column. Nevertheless, if I do the change in y over the change in x, I get the same thing, 0 divided by 2, which gives me a slope of 0. Remember, what does a slope of 0 mean? It means that you've got a horizontal line like this at the value of y equals 2. So a slope of 0 is totally flat. You're not going uphill, you're not going downhill, totally level. Let's look at one more example here. We have, let's see, going from negative 3 to negative 3, that's a change in 0. All of these are the same, so these are all changes in 0. And our change in y, let's see, this is going up by 3, this is going up by 3, this is going up by 3. So if we do the change in y divided by the change in x again, the change in y is positive 3, and the change in x is 0. Now, hopefully you remember this from earlier math classes, but division by 0 is not possible. This is undefined. This has an undefined slope, and if that isn't something that you remember, if you plug it into your calculator, you will get an error message. 3 divided by 0 gives you an error message on your calculator. So this is an undefined slope, and the reason it's undefined is because this is not a function. This, when the x value is always constant, is a vertical line here at x equals negative 3. And this isn't a function because it fails the vertical line test. As I move my pen across the graph, my pen hits that graph in more than one point when I'm at x equals negative 3. Before I move on to look at different types of slope, I would just like to point out that you can also use the slope formula when you're given a list of points. So going back to example A here, I can choose 2 points. I could call this point 1, and I can call this one point 2, and I can do y2 minus y1, so 14 minus 20, over x2 minus x1, 7 minus 4, and that gives me negative 6 over 3, which still gives me negative 2. So by far the most useful method for calculating slope is actually this slope equation, y2 minus y1 divided by x2 minus x1, because it works on graphs, it works on lists of data points, it works in a variety of situations, so long as you have 2 points. I could just give you 2 points on the graph and you could calculate the slope between them. Let's look at types of slope one more time, just so that they're all summarized in one place. Our positive slopes, the line rises as you move from left to right. A negative slope, the line falls as you move from left to right. If you have a zero slope, the line is totally level. There's no hill at all. The line is horizontal. And an undefined slope, the line is vertical. One way that I remember that the undefined slope, the slope that's undefined is the vertical one, is that's ground that you cannot walk on. You can walk up a hill, you can walk down a hill, you can walk on level ground, but you can't walk vertically. So that's the one that's undefined. One other point is if you do have a negative slope, it doesn't matter where in the fraction you choose to write the negative sign. You can write the negative sign on top, you can write the negative sign on the bottom, you can write the negative sign out in front of the fraction. These are all equivalent ways to express a negative slope. And lastly, if you ever have a whole number slope, you can think of it as being over the number 1. So the rise, or in this case the fall, is negative 2 for every 1 unit of horizontal movement. The 1 isn't written there because we write fractions in simplest terms, but it is implied. So let's go in the other direction now. How about I give you equations and you put them on a graph? How do you plot graphs using slope-intercept form? Well, M is the slope and B is the y-intercept. So we can use that information to help us out by kind of looking at the equation and deriving some information about it. So looking here, I see that my y-intercept is negative 4. And my slope is 3. My slope is positive. So I'm going to start low on the graph at the negative 4 region, and I'm going to move upward. So I want to, let's see, I'll leave a little bit of room to the left, and I want to be about, I want to leave plenty of room down below because I'm starting down here at negative 4. This is my negative 5 value. And I'm over here at negative 2, up here at positive 5, and over here at positive 8. So if I start down here with my negative 4 as my y-intercept, then I can use my slope to plot additional points. And so remember, a slope of 3 means for a rise of 3, 1, 2, 3, I go to the right 1. This is a positive slope, so I'm expecting my line to go up and to the right. Those points are kind of close together for me to draw, although 2 points determine a line, and it should be enough for me to draw a line. I like to have a few more points that cover a little bit more of the graph. So I'm going to just continue my pattern of going up 3 and over 1, up 3 and over 1. And now I feel like I've got enough points to give me a fighting chance at drawing a straight line. There we go. And that is the graph of y equals 3x minus 4. So our strategy here is to plot the y-intercept, then use the slope as information to plot additional points, and then draw a straight line between the points. How about this equation, y equals 6.5? Is this in slope-intercept form? Well, yes, it is. It's just that the x term disappeared. Why did the x term disappear? Well, our slope must be 0. So if I were to rewrite this in more obvious slope-intercept form, it would be 0x plus 6.5. So I can see a little more clearly now that my y-intercept is 6.5, but my slope is 0. So what does that look like on my graph? I can be kind of in the middle here with my y-axis, but I need to be a little low with my x-axis because I need to be able to go up to 6.5. So I'm going to have -5, +5, -2, and +8. And now I can plot my y-intercept is here at 1, 2, 3, 4, 5, 6.5 right here. But I can see that with a slope of 0, I never move from that 6.5. I'm 6.5 no matter where I am on the x-axis. So this would be correctly drawn as a horizontal line like this. Let's look at the next example. This says use the slope and y-intercept to graph -5x minus y equals -2. Notice that this is written in standard form, and we learned last class how to graph equations in standard form. But this is all, but this example is asking me to use slope and y-intercept to graph it. So I need to rewrite this equation so that y is all by itself on one side of the equation. Writing a linear equation in slope-intercept form is the same as solving a literal equation for y, getting y all by itself on one side of the equation. So how do I do that? Let's see. Y is being subtracted from -5x over here. So I'm going to go ahead and add 5x to both sides of the equation. The -5x plus 5x is 0, so if I'm adding or subtracting 0, it doesn't do anything to the equation. So I'm left with -y equals -2 plus 5x. But if I have -y, that isn't having y all by itself yet, so I need to get rid of the negative. So, and I'm going to do that by multiplying both sides of the equation times -1. That cancels out the negative sign here, so I just have y left on the left side of the equation. And on the right side, I need to remember to use the distributive property here. It's not just -1 times -2, it's -1 times -2 as well as -1 times 5x. So -1 times -2 is +2. And -1 times 5x is -5x. So my completed equation is y equals 2 minus 5x. I now know my y-intercept, and I now know my slope. So I can plot my graph. Because this has quite a large negative slope, and I start at 2, I'm just going to make my x-axis a little bit low. I'll keep my y-axis in the middle here. So I'm going to go from -5 to 5 on the x-axis, and from -3 to +7 on the y-axis. And I'm going to start by graphing the y-intercept at y equals 2. And because this has a negative slope, I'm expecting a downward slope as I move to the right. So when I go to the right one, I go down 1, 2, 3, 4, 5. There's one of my points on the line. And I can draw a point going the other direction as well. If I go to the left one, if I go negative in the x direction, then I go positive in the y direction. 1, 2, 3, 4, 5. So if I do my best to connect those dots with a straight line, that is a graph of -5x minus y equals -2, but I did use my slope-intercept form to graph it. Just so that we're clear on the slope here, this is a slope of -5 over 1. You can think of that as -5 over 1, or you can think of it as +5 over -1. And that might help you put a point down here to the right of the y-intercept and up here to the left of the y-intercept, if you think about the slope in both of those ways. All right. How about writing a graph from a verbal description? If I tell you that a linear function g models a relationship in which the dependent variable increases 3 units for every 1 unit the independent variable increases, what does that mean? The dependent variable depends on the other variable. The dependent variable generally refers to y. The dependent variable refers to the y variable. And the independent variable refers to x. X is the thing you choose to plug into the equation, and then y comes out as a result. So I'm telling you that y increases 3 units for every 1 unit of x. So if we talk about the change in y over the change in x, these are both increases, so they're both positive numbers. The change in y is 3 for the change of x of 1. So I'm basically telling you that the slope here is, the slope is 3. So from this verbal description, you can figure out that the slope is 3. So let's kind of put this on the graph, because I also give you a starting point. I tell you that if x is 0, if I plug 0 in for the value of x into this function g, we have a value of 3. So I also know my y-intercept. So if I put a dot here at 3, I guess I should label my numbers. This will be -5, +5, -5, +5. And if my slope is 3, well, I don't have a whole lot of room in the up direction, but I do have a bit more room in the down direction. So I can go for every 1 unit horizontally, we go down 3. For every 1 to the left, we go down 3. And if there were room, I could go up to the right, and to the right 1 and up 3. So my graph looks like this. Okay, and I just got that from reading the problem. This gave me the y-intercept, and the slope was 3. I guess I should have written that in here. The slope is 3 from doing this calculation, 3 divided by 1. I'm also asked to identify the intercepts of the graph. Well, we already identified the y-intercept. The y-intercept was at 0, 3. However, we can also now figure out the x-intercept, and I can see from how I drew my line that the x-intercept is right here at -1, 0. Let's apply this to a real-life problem now. A submersible on the ocean floor ascends to the surface. If h of t is the submersible elevation in feet, t minutes after starting to ascend, this equation models the ascent. H of t equals 650t minus 1300. Let's take this apart and figure out what each of these components of the equation mean. Slope-intercept form works well for linear equations when the word problems have one rate and a starting value. Here I have a rate, and my rate is 650. That represents So this says interpret the slope here in this question. That represents how quickly I'm ascending. It's how many feet I can ascend in a minute. 650 feet per 1 minute. Notice that a rate mixes units, feet per minute, or miles per hour, or dollars per ticket. All of those are rates because they combine different units. So the slope in y equals mx plus b form, that slope has this meaning of how many feet per minute, the speed of the ascent, the speed of ascending. Okay. Now, I seem to have a starting value. My starting value is represented by b. So it's this 1,300, negative 1,300 here. What does that mean in the course of the problem? Well, this is all about feet. How many feet that the position of the submersible in feet below sea level. And so this must be my starting point. The submersible must have started at negative 13,000 feet below sea level. So the y-intercept represents the starting point, the starting depth of the submarine. About the meaning of the x-intercept. The x-intercept is going to be, remember the x-axis is going to be like the t-axis here. So that's going to be the number of minutes it takes the submarine to get up to 0 feet, to fully ascend from its current depth. So the x-intercept is the time it takes the submarine to reach a depth of 0. Okay. All right. So now that I know that the highest value, my depth, the elevation can be is 0. So I'm going to plot my origin so it's here in the top left corner. I can have positive values of time. I'm only going to have negative values of elevation going all the way down to negative 13,000. And if I make each tick mark worth negative 2,000, I will be able to get down to 13,000. So I'm going to not label every single one. I'll do negative 4,000, negative 8,000, negative 12,000, negative 16,000 is plenty. And then in terms of time, I don't really know how much time yet this is going to take me, but I'm going to, let's see, I'll just go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28 minutes should be enough for this example. Time in minutes. And let's plot my, just like before, we're going to start with our y-intercept. So I'm going to put a value, let's see, this mark between 16,000 and 12,000 is negative 14,000, and I want negative 13,000. So this is my actual y-intercept. Now, my slope is 650. It's positive, so it's going to kind of go up and to the right. But 650 is a really kind of odd number. I don't really want to go over 1 and up 650 because that would be hard to measure on this graph. So instead of going over 1, I'm not just going to go over 1, I'm going to go over 10. I'm going to go 10 to the right because if I go 10 to the right, each one step should take me 650 feet upward. 10 times 650 is 6,500, and that's a much easier number to find on my graph. So if I start at 13,000 and I go over to the 10 mark, I should go up 6,500. And going up 6,500 takes me to 6,500, negative 6,500, because 6,500 plus 6,500 is 13,000. And so this is my second data point here. And since I already know that going up 6,500 feet took 10 minutes, I can do that again and go my remaining 6,500 feet takes me over here to 20 minutes. So if I draw my line of best fit here like this, or the line described by this equation, this line with a positive slope of 650 and a y-intercept of negative 13,000 looks like this. And that x-intercept, it takes 20 minutes. It takes the sub 20 minutes to reach that ending depth of 0 meters. The starting depth of the sub was negative 13,000 feet. And the sub increased in elevation with a rate of 650 feet per minute. So we've graphed the function, but we haven't mentioned the domain and the range yet. So the domain, remember, has to do with x, but we don't have x in this problem. We have t. So what values can we use for t? Well, of course, it doesn't make sense to have time be a negative number. We can't have negative minutes. So our t value must be greater than 0. But in this problem, the submarine doesn't run after 20 minutes because after 20 minutes, the submarine is back up to sea level. So our ending value is at 20 minutes. For the range has to do with our y values, which are here, or h of t values. These are our depths. And our depths here, our lowest depth was at time 0, and that was at negative 13,000, is the lowest value for h of t. And our biggest value was when we got up to 0, at a depth of 0 meters. That is our highest value for the range. I hope this helped.